Hello, this is the second part for Module 10, Graph Coverage. So continuing from the previous module, after you have understand what are graphs, what are the components of the graph, including nodes, edges, and the paths, we're gonna talk about graph coverage criteria. So we're gonna use the knowledge that you learned from the previous part to define several criteria that we can apply the testing on the graph structure. Okay, so let's get started. The graph coverage criteria is the process that we need to define test requirements, okay, or we call them TR, in terms of the property of the test parts in the graph G that represent a software that we want to test, right? Represent software we want to test. So the steps are as follow. First, we need to develop a model of the software as a graph. So we need to turn the software that we have into a graph first. The software may be the method that you want to test, okay? Or usually it's a method. You cannot define the whole program. The graph will be too large. And second one is we define the test requirement. And then we make sure that the test requirement is met by revisiting the particular node or edges based on some parts. We have been using the word test requirement, so I would like to explain a bit what it is. So the test requirement is the properties of test parts, okay? And the criteria or the test criterion is the rules that we use to define the test requirements. So think about the test requirement as something that the test that you create must satisfy. Okay, go back to the concept that we learned from the previous week about coverage criteria, right? We need to have some test requirements, like the candies. You want to cover all the colors in the candies, or you want to cover all the flavors of the candies. Those are test requirements. So when we turn that into graph, the test requirements would mean the paths, the nodes, the edges, anything that we can satisfy by running all the test parts that we have, okay? So the satisfaction of the graph coverage criteria, okay, I'm talking about satisfaction here. Satisfaction is defined as follow. So if we have a set of test requirements for any criterion C, and we have a set of tests T, the set of tests T will satisfy the criterion C if and only if every test requirement in TR, there is a test part in the path T that meets the test requirement TR. Okay, so to simply put, we have the test, and this test satisfy all the test requirements in the set of test requirement. So it's like a checkbox that you have test requirement TR1, does we satisfy it? TR2, does we satisfy it? TR3, do we satisfy it? So on and so on. All right. And this kind of graph coverage criteria, you have two types. The first one is called structural coverage criteria that we depends on the structure of the graph. We're gonna discuss this in this module. The second one is data flow coverage criteria, where we care more about the flow of data in graph. Okay, we're gonna discuss this in the next module. Okay, so with the data flow coverage, you need a bit more understanding of how it works. So we're gonna leave that for now, and we're gonna focus on this one for the module today. Okay, so in the structural coverage criteria, we have 5 types of coverage criteria: node coverage, edge coverage, edge pair coverage, complete path coverage, and prime path coverage. While for the data flow coverage criteria that we're not going to look at today, there are three types of coverage criteria: all depth coverage, all uses coverage, and all DU path coverage. All right. So let's start with the first one. The first one is called node coverage. So for node coverage, we define the coverage as follows. The test requirement must contain each reachable node in G. Okay, each reachable nodes. Or we can say TR contains all the nodes in G. Okay, this is a simpler version, but it needs the word reachable so that you can actually reach all the nodes, and we only take that reachable nodes into account. But usually, if your graph doesn't have any issue, you should be able to reach all the nodes. Okay, so the simple version would be you want to go through all possible nodes inside this graph G. Okay, so if we have this graph, the single entry, single exit graph, we have these 7 nodes, 1, 2, 3, 4, 5, 6, 7, and we have the following edges. The test requirement is here. You can see that it covers all the nodes that we have. 1, 2, 3, 4, 5, 6, and 7. So how to satisfy this node coverage criteria? We need to find test paths that cover all the nodes. So I start with this test path first. Okay, test path P1. I go to node 1, 2, 4, 5, 7. So I go to this 1, 2, 4, 5, and 7. Okay. The second one, I have this test path P2. I'm gonna go through 1, 3, 4, 6, 7. So I go to 1, 3, 4, 6, and 7. So you can see that all the nodes in the graph has already been reached by these 2 test paths. Okay, so if we have this test set of T contains T1 and T2, that the path of T1 equals to the test path P1, and the path of T2 equals the test path P2, we say that T satisfy node coverage on G. Okay, you can also find other kind of test paths as long as it cover all the nodes. Okay, so I'm gonna give you another set of potential test path. You can have 1, 2. Oh, sorry. In this case, you cannot, right? So there are only 2 test paths that are available here. Let me think a bit. So yeah, okay, you can. So you can have test path P1, 1, 2, 4, 6, 7, and another test path P2, which is 1, 3, 4, 5, 7. Okay, you can see that these 2 set of test paths are not the same, but both of them cover all the nodes in this graph. So this one, 1, 2, 3, 1, 2, 4, 6, 7, 1, 2, 4, 6, 7, and the other one, 1, 3, 4, 5, 7. So 1, 3, 4, 5, and 7. Okay, so either this one or this one, they both satisfy the node coverage criteria on the graph G here. The second one is called edge coverage criteria. You might guess from the name that this one, we need to visit all the edges in the graph. So for the edge coverage criteria, the test requirements contain each reachable path of length up to 1 inclusive in G. Okay, the definition might be a little bit confusing, but when we say each reachable path of length up to 1, we actually means an edge, right? So you have a path of length only 1, so you need to have 1 edge in that graph. The path that have the length of 1 would look something like this, right? So we need to cover each edge in the graph. But it says length of up to 1 because we want to allow for graph with only one edge, only one node and no edge as well. So even though you have the graph that looks something like this, okay, remember that we discussed this last time, that it's also a valid graph. We can still apply edge coverage criteria there, okay, but the test requirement just doesn't have any edge. Okay, so we have the same graph, single entry, single exit graph. We have the same set of nodes and we have the same set of edges like the previous one. The test requirements contain all the edges. So it must contain this one, 1, 2, 1, 3, 2, 4, 3, 4, 4, 5, 4, 6, 5, 7, and 6, 7. So you list all the edges in the test requirement. Okay, and then we do the same. We find the test path that visit all the edges in the test requirement. So I have this first test path, 1, 2, 4, 5, 7. So 1, 2, 4, 5, 7 visit the following edges: 1, 2, 2, 4, 4, 5. Where should I put a tick here? 5, 7. And the second test path, 1, 3, 4, 6, 7. 1, 3, 4, 6, 7. This one visits 1, 3, 3, 4, 4, 6, and 6, 7. So with these two test paths, we already satisfy the edge coverage criteria. So if we have any test set T consisting of T1 and T2, and the path T1 consists of this test path, the path of T2 is this test path P2, then the test set T satisfy the edge coverage on this graph G. Okay. Although the node coverage and edge coverage may look very similar because you try to cover everything on the graph, but there are some differences here. Look at this graph. Let's analyze it. We have three nodes, 1, 2, and 3. Okay. There are 3 edges, this one, and this one. So the set of node is this one, and the set of edges is this one. Let's say if we do node coverage criteria, we would have the test requirements of 1, 2, 3. And we can use the test path 1, 2, 3 by going this way. Just a moment. Going 1, 2, and 3. And then we are done, right? Just one test path can visit all the nodes here. But if we think about the edge coverage, we need 1, 2, 1, 3, and 2, 3. So we need to cover all these 3 edges. And now just one test path is not enough. So we need to have the first one, 1, 2, 3. But we're still missing this one. So we need to add another one, 1, 3 as well. So you can see that the node coverage is slightly easier to be covered than the edge coverage. And they are different when you have an edge of another subpath. You have an edge and another subpath of a pair of nodes. For example, you have this pattern of an if-else statement like this. So whenever you have the branching out, then the node coverage will not be the same as the edge coverage. In the case that you cannot find the same test paths to satisfy both criteria at the same time. All right. Okay. The third one is called edge pair coverage, or EPC. So EPC says that the test requirement must contain all each reachable path of length up to 2, inclusive in G. Okay, so this one increases the length from the edge coverage. So length up to 2, this means, actually it means a pair of edges, but it allows for the graph that also have less than 2 edges as well. So again, the test requirement will doesn't have anything, but it is applicable to the small kind of graph that has less than 2 edges. What are the edge pair? So if we have this thing, 1, 2, 4, you would have an edge pair of 1, 2, 4. Okay, it's a pair of 1, 2, and another pair of 2, 4. So this one you have 2, 4, 5, and you have a pair of 2, 4, and 4, 5. Okay, makes sense. So, oops, sorry. So with this kind of graph, we will have the following test requirement. You have 1, 2, 4, which is this one, 1, 3, 4, which is this one, 2, 4, 5, which is this one, 2, 4, 6, which is this one, 3, 4, 5, which is this one, 3, 4, 6, which is this one, 4, 5, 7, which is this one, and 4, 6, 7, which is this one. To cover this, just only 2 test part is not enough anymore. So we have 4 test part here. So let's see the first one. I go 1, 2, 4, 5, 7, 1, 2, 4, 5, 7. I visit each pair 1, 2, 4, 2, 4, 5, 4, 5, 7. The second one, I go to 1, 3, 4, 5, 7. 1, 3, 4, 5, 7. So 1, 3, 4, 3, 4, 5, and 4, 5, 7. The next one, 1, 2, 4, 6, 7. So 1, 2, 4, 6, 7. I visited 1, 2, 4, 2, 4, 6, and 4, 6, 7. And the last one, I go to 1, 3, 4, 6, 7. So 1, 3, 4, 3, 4, 6, and 4, 6, 7. Okay, so by having these 4 test parts, if we can find a test set that follow these 4 test parts, then we satisfy the H-pair coverage. Okay. The next one is called complete path coverage. This means you want to cover all the parts in G. Okay, this is pretty comprehensive coverage, and it might not be applicable in many cases. So let's say if we have this graph, and we have the following 7 nodes, and we have the following 7 edges. Can we cover them? Let's see. So we have the test part P1. Okay, going to 1, 2, 3, 4, 7. The second one, 1, 2, 3, 5, 7. And the next one, 1, 3, 4, 7. And the last one, 1, 3, 5, 7. Oops, sorry. 1, 3, 5, 7. We need to check whether these cover all the parts that you have in the graph or not. Okay, so if we do, if we try to list all the parts here, let's try to list them. Okay, I think I just call them the test requirement, right? Okay, so the TR will contain the part 1, 2, 3, 4, 5, 6, 7, and then you have the part of length 1, 1, 2, 1, 3, 2, 3, 3, 4, 3, 5, 4, 7, 5, 7, and then we have length of 2, 1, 2, 3, 1, 3, 4, 1, 3, 5, 2, 3, 4, 2, 3, 5. So we keep listing all the parts. As you can see, there's a lot of parts according to each size of the parts here. But you will see that by listing all the parts, this set of test part will satisfy the CPC. Okay, how do we know it's satisfying? So let's say if you go through part 1, 1, 2, 3, 4, 7, not this one, it will cover 1, 1, 2, 1, 2, 3. And then you keep doing this 2, 3, 4 as well, 2 as well, 3, 4, 7, 2, 3 as well, 3, 4 as well, 4, 7 as well. Yeah, and then you keep doing this, you will see that these 4 test parts will cover the CPC. But however, when there are more complicated graph, like when you have a cycle like this, then the number of complete part is unlimited. Okay, with this graph, you will see that the node coverage would have test requirement of just 1, 2, 3, 4, 5, 6, and 7, and you can find 2 test part to cover that. The edge coverage, you would have this, and this, and this, and you can have also 2 test part to cover that. For the edge pair, you get a few more, but you still can find the test part. However, for the complete part coverage, you can come to this, and then you keep going 1 time, or you can repeat this 2 times, or you can repeat this 3 times, so on and so on. So the number of parts that are available in this graph is infinity, right? So the TR here is actually a lot, and it goes to infinity because you can keep repeating that cycle over and over. So the complete part coverage is not actually a very good one because you cannot define the limited set of test requirements. So how do we do this? So if you have a graph with the loop, now we already talked about this, we're gonna have a lot of test part that never be enough. So it's impossible if the graph has the loop because we have an infinite number of parts. That means also infinite number of test requirements. There are many studies that try to handle this kind of loops in graph. So in the late 1970s, people proposed to execute the cycle only once, okay? And in 1980s, execute each loop only exactly once. 1990, execute loop 0 time, 1 time, and more than 1 time. In 2000, we have a new concept called the prime path. And then we use this prime path to define the test requirements. Okay, so let's see how this prime path works. We're gonna follow the concept of prime paths, and we're gonna see what's the definition of the prime path now. To understand the prime paths, you need to understand the simple path first, okay? So simple path is a path from node Ni to node Nj when there is no node that appears more than once, except that it is the first and the last node in the path. So this means we don't want any internal loop inside the path, but we allow the loop itself, something like this is okay. 1, 2, 3, 1. So only the first and the last can be the same, but this is okay. We cannot have something like this, 1, 2, 3, 1, 2, 1, 3, like this, because you have 1 appear more than once, and they are not the first and the last node. Okay, this means you got something as a cycle here, right? Because you come back to the same node again. Okay, so if you understand what a simple path is, then we can move on to the prime path. The prime path say it must be a simple path, but it must not be a proper subpath of any other simple paths. So it means that we need to find all the simple path first, and then we remove the one that are subpath of other simple paths. And what left remaining are called the prime path. Think about it as a prime number that it cannot be divided by any other numbers. Now it's pretty similar concept. So let's say if we have this graph, and if we list all the simple parts, we would have the following set of simple parts. Okay. This part, do they have a cycle? Yes, we have a cycle here. So we allow 1, 2, 4, 1 to be in our set of simple parts. and also 1, 3, 4, 1, and also 2, 4, 1, 2. You can see that they have the same starting and ending node, but they don't have these appear inside the path. Okay, so they are all simple paths. How do we find the prime path? We check whether if this simple path is a subpath of any other simple paths. So 1, 2, 3, 4, they are actually not a prime path because they are subpath of all the paths here. 1, 3 appear in here, so they are not prime path. Let me erase this. 2, 4 appears here. 3, 4 appears here. 4, 1 appears here. Okay, so they are not prime path. 1, 2 appears here. 4, 1, 3. Let's see. 4, 1, 3 appears here. 4, 1, 2 appears here. 3, 4, 1 appears here. 2, 4, 1 appears here. 1, 3, 4 appears here. 1, 2, 4 appears here. 4, 1, 3, 4 cannot find anywhere. 4, 1, 2, 4 cannot find anywhere. Yeah, and I think that's it. So we get rid of these set of symbol parts that are subpart of the other symbol parts, and then we get this list, final list of the prime parts. Okay, and you can see that these prime parts, they are not a subpart of any other parts. So if we apply this concept to the previous graph that we have seen before in the complete path coverage, we will see that we start by listing all the simple path first. And in this graph, we're going to get 31 simple paths. Okay. And then we get rid of the one that are subparts of the other. So 1, 2, 3, 4 appears here. 1, 2, 4, 5, and 1, 2, 3, 5 appears here. 2, 3, 4, 7 appears here. 2, 3, 5, 7 appears here. 2, 3, 5, 6 appears here. 1, 2, 3 appears here. 1, 3, 4 appears here. 1, 3, 5 appears here. 2, 3, 4 appears here. 2, 3, 5 appears here. 3, 4, 7 appears here. 3, 7, 5. 3, 5, 7 appears here. 3, 5, 6 appears here. For 1, 2, 1, 3, 2, 3, these are pretty simple ones. So it appears in the others. So if we check that, we would get the final set of prime path, which consists of these three parts, and these three parts. So finally, you would have 9 prime path. Okay. So with these 9 prime path here that we see last time, we can see that this one execute the loop 0 times, okay? Because 1, 3, 5, 7 come this way. This one 1, 3, 5, 6 go this one, so it execute the loop only once. And this one 5, 6, 5 and 6, 5, 6, it execute the loop more than once. Okay, but we don't have the limited number of paths to cover anymore compared to the complete path coverage. So we have this last type of coverage called prime path coverage. So the prime path coverage say that the test requirement will contain all the prime paths in the graph G. This is a simple and elegant criterion because we get rid of the problem of the loop. Okay, we cover the loop, but we cover them only once and we don't go forever. We also reduce the number of test requirements to be limited and not so many. It will tour all the subparts starting from length 0, 1, so on and so on. So this one subsume the node and the edge coverage as well, but it does not subsume the edge pair coverage. Okay. So when the case that it does not subsume the edge pair coverage is as follow. If you have an edge, a node that has an edge to itself, like this case, when you do EPC, you would get NNM, which is this, and also MNN. So you can have this thing and this thing, right? So you can see that these are not a prime path. So the path that you must visit in some paths that you must visit in the edge pair coverage, they are not prime. So you cannot include them in the prime path coverage, while in the edge pair coverage, you would have them as a test requirements. Okay, so for this graph, EPC would contain 1, 2, 3, and 4 test requirements, and PPC would have only 2 test requirements. Okay, so the next concept is the touring, the side trips, and the detour. Okay, in some of the cases, if you want to get the test path that visit all the paths in the test requirements that you have, sometimes you cannot just go directly according to those paths. The definition of the subpath or touring say that any test path P will tour a subpath Q if Q is a subpath of P. So if you have this prime path 1, 2, 3, 5, 6, I show it here 1, 2, 3, 5, and 6. To be able to tour this prime path, you have to go this way only. Okay, and your test requirement, your test path will also be 1, 2, 3, 5, and 6. Okay, but in some of the cases, we cannot do that due to some restriction or some of the code that we cannot get that kind of straightforward execution. So we can relax this definition a bit. So if we cannot directly tour, we can tour with a side trip. So tour with a side trip means we have a test path T that goes through the subpath Q with a side trip, as long as every edge in Q is also in P and also in the same order. To put it another way, the side trip is the tour that can include the other nodes as long as it come back to the same node. Okay, if you want to tour the same path, prime path 1, 2, 3, 5, and 6, I can go this way 1, 2, 3, 4, 3, 5, 6. So this part is called a side trip. It's like when you go for a trip and then you visit something else that's not in the plan, right? So the path that you have with the side trip is 1, 2, 3, 4, 3, 5, and 6. And this will be your side trip part of your path. Okay, so if we allow this graph to be tour with a side trip and with this test requirements, you can have this test path that satisfy the side trip. The last one is called a tour with detour. So a tour with detour is slightly different. It's the test path T that tour a subpath Q if every node in Q is also in P in the same order. Okay, the first one say every edge, right? But this one we care about the node. So as long as it comes back to the prime path at the successor where it gets off, then it's okay. How does it work? I think easier to see with an example. So you have 1, 2, 3, 5, 6 as your test requirement that you want to satisfy. We can go 1, 2, 3, 4, 5, and then 6. Okay, you can see that we do not come back to the same node, but we go straight from here to here. Okay, so this part is called a detour, which is also similar to when you go for a trip, you visit something else, and then you don't come back to the same location, but you just go to the next destination directly. So with this, we would have a test path of 1, 2, 3, 4, 5, and 6. Okay. And this one will be your detour. Okay. Compared to this, we will see that we have additional node 4 that we add into the path. But the order of the node is still the same. 1, 2, 3, 5, 6. 1, 2, 3, 5, and 6. All right. So this is called the tour with the detours. So in some of the test requirement, if we say that we allow the test path to do side trips or detour, then you can consider this kind of situation as well. So in some cases in practice, you might find some invisible test requirements. So these are the test requirements that you cannot satisfy, might come from unreachable code or the subpart that execute with some contradiction, which also impossible to go. So with this case, we will try to do as much as possible. Okay. So if we can do side trip, then we try to do side trip. If we can do detour, we can do detour. So this is called the best effort touring. So we try to satisfy as many test requirements as much as possible without the side trip first. And then we start to allow the side trip or the detour to be considered so that we add. So that's all for this module. I want to summarize what we learned. So the first thing is we discussed the basic concept of graph. We discussed what are nodes and edges, what are paths, what are the reachability, and what are the concept of test paths. And in the later part, I discussed graph coverage criteria, including node coverage, edge pair coverage, complete path coverage, and prime path coverage. So that's all for the module. And in the next module, we're going to discuss the data flow graph coverage criteria. See you in the next module.